I'm like writing things that aren't on there.
All right.
So check it once in a while. Why did I draw 2Al plus 3s and 3 SO4 minus 2?
Because
Who used the erasers?
I did not.
There's a bunch of crap all up on here.
Oh my
Come on
Lord,
now.
people.
Courtney. Actually, probably Colin.
No, it wasn't me, man. I used that book over there.
Hey, I'm just putting
I
things
found a
back where I
logbook,
found
too.
them.
You did. It's all right. It's just the issue is gets on my hands and on my face or something. Remember my math teacher, one of my math teachers in high school. I can't remember her name, but she used to, I don't know, we used to joke that she used to eat chalk.
Oh, she was a mean teacher.
Well, she just constantly licked her fingers, so she would like do this, this, and this, or whatever on the board, and then lick her fingers.
Oh.
And then she would get it like on her face and hair. She was kind of like crazy. But she would always touch the board and then like touch her. I don't know. But anyway, what's going on?
I said I picture Miss Skip.
All right, that's an official recording now. I really can't remember the teacher's name. I liked her. A lot of kids didn't like her because she was kind of mean and a little crazy and intense. But I liked her. She was genuine. She really liked math, and I was like, all right, well, that's her thing. That's fine.
Genuinely chalk.
Back to this. You can eat chalk, actually. Chalk is calcium carbonate. You can actually eat that. Yeah. So if you have a little tummy ache, Matt Payne, just chomp on some chalk.
I eat Tums all the time.
There we go. Now, why 2 ALs again?
Because in the equation it says
Because there's 2. Okay, yeah. Al2. All right, now time to focus. Al2, SO4, 3. So there's 3 dissociated ions here, 2 dissociated. So this is 5 particles that this would produce. Yes.
So if you had to write it, if you had to do the diagram, you have to do all
No.
of them.
I did it just to show you that's really what would happen. But if this was like a test question, they would say just draw one ion of each or something to that effect. They would tell you exactly what to do. You wouldn't have to draw all 3. So anyways, you guys all, I think from what I can see, did this right. Oxygen faces the positive, hydrogens face the negative. Again, that's another thing I don't think anyone's going to get wrong at this point anymore. All right. Okay, now on the front, you were supposed to draw how those 4 dissociated. Now, letter C does not dissociate. Did I tell you that?
No, I can't.
I didn't tell you. Okay, I told the other class. Sorry. So, PbCl2 dissociates into Pb plus 2 and 2Cl minus.
Wait, so would you put the AQ though?
Yeah, you're supposed to. I'm just being lazy. You're supposed to put AQ and AQ after those. Now you would have 2Al plus 3 SO4 minus 2. Now, letter C does not dissociate at all, so you would just get C12H22O11AQ. So this one doesn't dissociate, it actually stays together. I'll explain that in a second. And then D, you get NaBr, you get Na plus, and Br minus. All right, so again, all of those on the right side are aqueous. I didn't explain this super well, so if you were confused, I can understand. But this is what I wanted you to do. The point of this is if you have a 1 molar solution of all 3, you will have 1 mole of Na plus and 1 mole of Br minus, right? So think of the stoichiometry here, the balancing. 1 to 1 to 1. So if I have 1 mole of this, that produces 1 mole of each of those. Okay, I joke with my AP class about 1 mole of marker equals 1 mole of cat. And that sounds like a really weird thing to say. But the point is, if I have 1 of these, then I have 1 of those and 1 of these. Together, they make 1 marker. The thing that you need to know in chemistry is if you have 1 compound, then you have 1 part of each part. 1 Na, 1 Br. Up here, it's different. If I have 1 mole of this, I have 1 mole of that, but 2 moles of Cl. Because there's 2 Cl's for every 1 PbCl2. That's why we balance. That's what balancing is all about. So if you're really not following me with the mole thing, that's fine, as long as you understand 1 of these produces 2 of those and 1 of those. You understand that? You're good to go. All right, so you should know the balancing thing here at this point. So what I was supposed to, or what you were supposed to do, is now look at the questions and pick which one would have the highest boiling point, lowest freezing point, who conducts, who doesn't. This one here produces 2 moles of particles, 1, 2. This one produces 1 mole, just 1. This one produces 5 moles. This one produces 3 moles. 2 plus 3 is 5. 2 plus 1 is 3. All right? So this one here, right here, that one has the greatest number of forces of attraction. There's more forces of attraction in this container of water, if these are all aqueous. There's more forces here because there's more particles. Colligative properties depends on concentration. More particles means higher concentration. So, any question that asks who has the highest boiling point, lowest freezing point, lowest vapor pressure, meaning it won't evaporate, it's this one. Okay, letter B. So let's see. 1, lowest freezing point, B, has the greatest number of particles. 2, least number of dissolved particles, that's C. It only has 1 particle. It only has 1. So whatever you guys were putting, if you were confused, that's fine. Make sure you're up here looking at me, listening, so you understand. This one has 1 particle. This one has 2. This one has 5. That has 3. So this one would have the least number of dissolved particles. The way sugar works is it doesn't break apart into C's, H's, and O's. The best way to explain... Oh, let me try and think of a good analogy that will help you. The best way to explain this is it's a group of molecules. I'm trying to think of... I can't think of...
That stick together.
Yeah, it's a group of molecules that stick together, and when you dissolve it, the molecules break apart, but the molecules stay together. Molecules break apart, but the molecules stay. I guess a real kind of gruesome way to explain it would be dissociating is when the compound breaks apart into little pieces. So I like to talk about dismembering humans for some reason. Okay, so if I was to dissociate, my legs and arms would fall off. That's when little pieces of me break apart. At least you with me on that, sort of, try and understand a little bit. That's what these 3 are doing, okay? But here, it would be like all of us together in one clump in the middle of the room, like maybe all holding arms or hands, and then when we break apart, we're still full, whole humans. Our arms don't fall off. So one of us is one of these. So we are not breaking apart, losing our arms and legs. We're not dissociating. That's what sugar does. It stays together, but it's a whole clump of them together, and then they break off into pieces, but those pieces are bigger pieces. They're called molecules. They don't break apart. They don't lose their parts. So that breaks apart. It's the best I could come up with off the top of my head right here. I didn't really think about it. Sorry. But that's the difference. So covalent, they don't break into little tiny pieces. They stay together. All right? So 1 mole of this, all right, is kind of the same as 1 mole of this, whereas this produces individual pieces, individual particles. So all you need to understand is, can you count? 2 here, 1, 5, and 3. That's how we answer number 2, for example. 3, who does not dissociate? That would be C. Just explain that. 4, lowest vapor pressure, letter B. Greatest number of forces of attraction. The ionic solution that has the least effect on the boiling point. So look up here. Ionic would be A, B, and D. A, B, D. So if you're following me and you're really trying to listen to what I'm saying, out of A, B, and D, which one would have the smallest effect on that solution?
D.
D, because it only has 2 particles. Colligative properties depends on concentration. The number of particles is the concentration. 2 here, 3, 5 there, and 3. So 2 would have the smallest effect. So for 5, that would be D. Yeah. 6, highest boiling point, B. Most particles. Melt ice at the quickest rate, B. It would lower the freezing point the most, the fastest, because there's more particles. Add a solute, freezing point goes down. This has the most solute in it. Solution that would take the longest time to evaporate. Eyes up here. It would be B again. These particles, there's 5 of them, have the greatest number of forces of attraction. They're like little anchors holding the water down. Water's attracted to them. You drew it on the back. Water's attracted. It's not going to evaporate. 3 moles of dissolved particles would be A. 1, 2, 3. Conduct electricity. A, B, D. They're ionic. Ions moving around in the water conduct electricity. Ones that do not conduct, covalent. Letter C. Letter C. Took me a little while to explain it. All right, hopefully that makes a little bit of sense. Questions? Okay. You got any notes? Got a little bit of time here. We got to talk about a few more things. We are done with colligative properties. Okay. All right, I got a list here. Oh, Henry's law. Yeah, we talked about Henry's law. Let me show you. I showed you that video the other day. Let me show you a picture. Lights, please. Let me show you this quick.
I got 7 out of 8 on this game. Those 1.5 and 1.5.
The video's kind of small. So in our notes, we're writing Henry's law. I know this is right here. My hand is not on in the thing, right?
No.
No. Okay. But this is?
Oh, yeah.
Okay. All right. So Henry's law. Write this down. Henry's law. That's the title. We already talked about it. We talked about the soda, the CO2 dissolved. Why do we keep the top on? So I'm going to explain this here again today, and then we will move on. It's not an incredibly difficult concept. Now, actually, before we get into that, I wanted to show you this to refresh your memory here. So on table G, why are these 3 lines decreasing with temperature? Remember, solids like KCl, NH4Cl, NaCl, KClO3, Ki, NaNO3, they all go up. This one, I think, is KNO3, goes up dramatically. Okay, the solubility increases dramatically when you increase temp. So now, and you saw it when you made the rock candy. You had a little tiny bit of water, and you dumped 400 grams of sugar. And I heard, some students saying, "This is never going to dissolve." They're probably joking, but it just looks like it won't. But it does, because as you heat it up, you can dissolve way, 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 way more in the same amount of water. You get that, okay? Water gains energy, and with that energy, it's able to dissolve more of the solute, break it apart. So what's going on with these 3, HCl, NH3, and SO2, as temperature increases, why does the solubility go down? Think about it for a minute. Yes?
Can I come in fourth grade
Yeah.
instead of third?
That's fine, whatever.
Can I come, do I have to come at the beginning?
Whenever you want. I'll just stop whatever I'm doing.
Okay.
It's only going to take you like 5 minutes, right?
Yeah.
Yeah. Okay.
Alright.
Yeah. What do you guys think? Why, when you increase temp, does the solubility of these 3 decrease? Because they're gases. Gases want to be cold to stay dissolved. Look how hot. Look at NH3 at 0 degrees. Solubility is 90. Okay. At 100, it's down here around 7 or 8. So the colder you keep gases, the better they dissolve. So that's one thing I want you to get out of today. Colder gases are, the more they dissolve. What does that have to do with this picture? There's something else you can do. You can put them under pressure. So it's a very simple diagram. You got a piston that can push, be pushed down and increase pressure, right? So as volume shrinks, pressure increases. You know that. So as this pressure is increased, the piston is going to be pushed in. These gas particles in the air above the solution are now pushed into the solution. So there's 2 things I need you to learn today, and hopefully you already get it from everything we've learned this year. As you increase pressure, gas solubility goes up, meaning you can dissolve more gas. And that's it. That's Henry's law. There's a fancy definition, and it's the solubility of the gas is directly proportional to the pressure of the gas above the solution. I mean, that's just kind of wordy. The point is, the higher the pressure up here, the more gas particles dissolve down here. That's what you need to know. Think of it as the air or the gas is literally pushing the gas into the solution. That's what the pressure is doing. It's pushing it down, stuffing it back into the solution so it can't get out. If you release the pressure, these red ones now can come out of solution. Okay? Soda, you keep the top on to keep the CO2 in the soda. Take the top off, you hear the psst. You release that pressure above the soda, CO2 is going to leave and it's going to become flat. So again, the 2 things I need you to understand. Henry's law is just about pressure. But the other thing I need you to understand is temperature. So we want low temp, high pressure. We already learned that. How do real gases become ideal? High temp, low pressure, so they can expand. think about it. If we want these gas particles in the solution, we want the exact opposite. We want to squeeze the gas particles together and keep them really cold because, like penguins, that's my analogy, goats or whatever you want to think of, when it's really cold, they huddle together. So you want cold temperatures to keep the gas together, more dense, likely to sink, and then high pressure, forcing it. All right, forcing it in a solution. So it's just a good picture. We're going to basically draw that. If you want to draw it, go ahead. I'll wait a minute before I turn this off. But we're going to put that in our notes. You might as well just copy that down. All right. You don't have to have the different colors. You can just do in the one with lower pressure. Just put just a few particles, and then when you draw it with the greater pressure, draw a lot of particles. That's all you need. You don't really need the different colors. I understand why they did that, but you don't need that. The point is, increased pressure, more get dissolved. Increased pressure, more get dissolved. And then we'll write everything down that I just said, and then we'll move on. Oh, again, you should, instead of just drawing too, you should be labeling, right? So this one here is high pressure, more gas dissolved. Low pressure, less gas dissolved. You guys ever played King of the Mountain? Even know what that is?
Yeah.
What?
Never.
Maybe it's called something else. Little kids play.
Yeah.
You get on top of a mount, like a little mound of whatever, snow, dirt, a hill,
And you start
and then
shoving kids
your
down.
friends try and take control of the hill. You have control, and your friends are trying to get you off it. So as soon as they come up, you literally throw them down the hill.
I think I did that. I think I did that in one of
That's
the
called,
huge
like,
snow
King of the
piles
Hill.
in like second
Yeah.
grade.
Yeah, I played all the time in the snow.
Yeah, in the snow, it's safer in the snow. You know, if it's nice out and
Played on rocks.
There's rocks. Yeah, just throw someone smash that in the rock, then they're not getting up.
Played on a pile of
But
glass.
why am I thinking of that? Or it just made me think of it. What's that have to do with anything?
No idea.
No idea.
Increased pressure, so when they fall, they break their nose.
Yeah, I mean, if you have a stronger, bigger person on top of the hill, that's kind of like a lot of pressure throwing everybody down the hill. You have a little weakling on top, it's not going to happen. Everyone's going to storm the hill. I don't know, I have weird analogies that make sense to me. Yeah, so it wouldn't work out so well for me, but maybe someone who was bigger and larger, it would work out for. I can't remember how. I used to probably get thrown around doing that, but that's all right. Are we good? Okay, so what's the two things I need you to remember before you get out of here? Lights, please. Somebody, lights, please. I'm just going to write this. For gases,
It's
Lower they are,
decrease
lower they
temp.
Olivia just said it. So, Olivia, go ahead.
As pressure increases, gases are more soluble.
As pressure increases on a solution, gases are more soluble. More soluble. You already have this, or you should. You just wrote it down from the pictures, but if not, make sure you understand this. Write it down. As pressure increases, so as you push down. So that was the picture on the right. Okay? So you have the piston way down here, and then here's your solution. The gas is getting pushed in. So more gas is dissolving here because you're pushing, increasing pressure. And then when you release that pressure, here's the piston now, here's your solution. Now the gas is going to start to leave. You're only going to have a few dissolved. So there's going to be more gas particles up here, less in the solution. And then the other thing is, we want to put this on ice. Want to put ice underneath it or around it. Okay, we want to cool it down. Low temperatures equals an increase in gas solubility. I don't really need to go on and on and on and on because we've already talked a lot about solubility, and I'm hoping you understand how solutions are formed. And this is just one little thing, one part of it, okay? So those 3 lines on table G going the wrong way. This is why. Lower temperature for gases is better. So on that graph, table G I showed you, as it gets warmer, this is happening. Gases are leaving, okay? So if you take the top off a bottle of soda and put the bottle of soda on the counter or in the sun, it's going to go flat very quickly, which, you know, for me, who cares, right? You shouldn't be drinking soda. But the analogy is to understand that. So if you put the top on, put it in the fridge, it stays fresher longer. Now, what else could you do to that soda? Think like real life. What could you do to that bottle if you want to keep it fresher longer? So you open up your 2 liter of poison, pour a little bit, okay? Soda level drops. What could you do to that to keep it fresher longer?
Bring it to the Arctic Circle.
No, in your house. This is like something real you can do.
Something real. Put it in the basement.
Oh, I know from my brother's.
Go.
Squeeze the bottle until like the soda's at the top.
That's right. So if you have a normal soda bottle, this is going to be a terrible drawing, so just bear with that. Okay. Normal. Okay, you drink it, drink a little bit, and then you put the cap back on. Great. Okay. Or, I don't know how I'm going to do this. Or you can squeeze it. All right. So you can squeeze the bottle. All right, stay with me. Squeeze the bottle. Now, when it's squeezed, you put the top on, okay, and then let go. It's going to stay that way. Do you agree? Do you understand that? Because it's basically creating a vacuum, okay? So you put the cap on. So here, your level of soda here, you have all this air that the CO2 can leave the solution because that's low pressure. It's a big space. Now, if you squeeze it, the level of soda is going to rise, correct? So maybe your soda is going to be here. You only have this much space. So, yes, some of the CO2 will leave, but once this fills up with gas, it will no longer leave, and it'll actually start to go back in the solution. So once this pressure builds, that was weird, this will stay dissolved longer. So you want little tiny space, okay? So that's one way you could keep it fresher. And the concept here, again, high pressure will keep more dissolved. That's why I bring that up. I personally, you should go home and just pour all your soda down and drink. That's what I think. But that's a different issue. So again, Henry's law is with the pressure above the solution. Listen, give me another minute here. Hey, Trevor. Tomorrow we got 2 more things to talk about with solutions, and then tomorrow we're going to start our new unit on kinetics and equilibrium. So new stuff tomorrow. I guess you don't have any homework. It's unfortunate.
Mr. McCoy, could you draw on a chalkboard with tongues? Like if you took a tongue